Okay, you all scan the QR code. I'll give you 5 more seconds. 5, 4, 3, 1. Okay, time's up. Okay, so on Monday, we sort of briefly introduced into the world of time series, and we discussed the distinction between cross-sectional and time series data. And we also sort of briefly discussed a very fundamental property of time series data, which is stationarity. So before we look into stationarity in a bit more details, let's quickly check whether you have graphs, what we've discussed on Monday. So the first question, well, the first statement, the order of observations does not matter for cross-sectional data, but it is essential for time series. Okay, this is a very simple one. And even without really learning anything about time series, you can't really get this one wrong, okay? This is a true statement, okay? The order of observations does not matter for cross-sectional data at all. Whether you rank me first or you rank yourself first doesn't matter, okay? There's no natural ordering. Whereas for time series data, okay, there is a temporal order. Yesterday happened before today, and today happens before the future. So there is already a natural ordering embedded in time series. Okay, so this is a correct statement. We don't care about ordering in cross-sectional, but we do care about ordering in time series, which makes the time plot make sense. Why do we even care about, the dynamic pattern when we plot the time series against time? Because there's an underlying pattern in it. Whereas for cross-section, it doesn't make sense to plot, let's say, for a given xi against the I subscript itself, because there's just no underlying pattern in this kind of, cross-sectional plot. Okay, so this is a true statement. Now, the next. Independence implies no autocorrelation. And remember, on Monday, we sort of briefly defined autocorrelation as if the correlation with its own past or future, okay? So it's a correlation within the series itself. In a sense, it's a correlation, but it's just not a correlation between two characteristics, okay? It's not the correlation between age and earnings. It's a correlation, let's say, about the age, well, not the age is something deterministic. It's about GDP, okay? The GDP today and the GDP yesterday, okay? And essentially, this is a statement about whether you think independence implies no correlation, okay? This is something you've seen in year 1 advanced stats. So this is a true statement, okay? Independence is the strongest form of no relationship, be it linear, nonlinear, okay? If two random variables are independent, basically it just means there's no relationship at all, okay? Whereas correlation, okay, defined statistically, that's about the linear relationship. We call from advanced stat covariance. Correlation, it's about whether two random variables move together linearly, whether there is a linear relationship among them, okay? If the two random variables are independent, obviously there's no linear relationship. So independence does imply no autocorrelation, okay? So this is true. Whereas the next statement, no autocorrelation implies independence, this is false, okay? Just as what I've said, no autocorrelation basically implies no linear relationship. But having no linear relationship doesn't necessarily imply that two random variables are not non-linearly related, okay? So no autocorrelation, or essentially no correlation is sort of the weakest form of no relationship. Okay, it only characterizes linear one, but independence takes both linear and nonlinear into account. So the weaker form does not imply the stronger one, but the stronger one will imply the weaker one. Okay, so this is a false statement. No autocorrelation does not imply independence because there could be nonlinear relationship. So this is the autocorrelation and independence. Now, the last statement is about the stationarity concept. So here it says stationarity requires the time series itself to be constant over time. And whether you think this is true or false, okay? So, oops. So this is actually a false statement, okay? Now remember, we say that stationarity is sort of like the formal definition of stability, okay? It's about the time series being stable. What does it mean by being stable? It means that the properties remain constant, but not the time series itself remain constant. Well, let's suppose we're looking at the GDP, okay? When we say that the GDP is stationary, it does not mean that we require the GDP today to be the same as yesterday, to be the same as a year ago, or to be the same as next year, okay? That's not what it means by stationarity. What we meant by stationarity is that the mean of the GDP series remain constant over time and the variance remain constant over time, which means the mean of the GDP last year is the same as the GDP this year, and the mean of GDP today is the same as the GDP tomorrow, okay? And if we think about the variance, that means the variance of last year is the same as variance of next year, okay? That is what it meant by the properties. The properties is about the properties of the distribution, the statistical properties, okay? The expectation, the variance, the covariances, the skewness, the kurtosis, but not the value that the series itself takes. We do not require the value of the series itself to be the same over time, but just the statistical properties to be the same over time. So this is a false statement, okay? Stationarity requires the statistical properties of the time series itself to be constant over time, but not the time series itself, okay? It's missing the statistical properties here. So this is a false statement. So these are just some few quick quizzes questions to quickly check what we've covered on Monday. Now, so just to briefly recap what we discussed, the key aspects of time series, okay? So we say that generally the time series, they are dependent, okay? So yesterday depends on the day before yesterday, and today depends on yesterday. That's generally always the case for time series data, and that the time ordering is important. So the dependency or the temporal order in this case in time series would allow us to make predictions based on own paths, okay, apart from taking into another time series into account. So if we look at the static model here, okay, this is essentially the same as what we've seen last term. Essentially, we're just regressing the output on capital and on labor. The T here, while it's a time index, there isn't really any time inside, okay? It's a static model because everything is sort of measured at the same time period. Okay, we're not taking into the past or the future into account. This is something we call a static model. And this makes perfect sense in cross-sectional because given random sampling, yi is independent of yj, okay? So let's say the output of factory 1 is independent of the output of factory 2. Therefore, whether we include the factory 2 on the right-hand side as another random variable doesn't matter at all because we already know that they're independent. Given that we know they're independent, it's just you know, it just doesn't really make sense, or it's just effortless to put it on to the right-hand side of the model equation there, which is why we don't model yi as a function of yj in cross-sectional, because we know they're independent. Now, in time series, okay, when we think about the output of today and the output of yesterday, in general, they are dependent. Okay? Whether we want to produce today might depend whether we have, you know, overproduced or underproduced yesterday. Then in this case, in order to take this dynamic pattern into account, it's very often that we consider a dynamic model where, apart from taking input, you know, the capital input and the labor input into the model equation, when we want to predict the output of today, we also include the lag of the output. Okay, let it be the one yesterday or the one a year ago or the one the quarter ago, depending on the context of your study. Okay, and this is one of the reasons why it's very important that we first of all study the properties of one time series itself. Okay, so what we've been doing for the first couple of weeks is that we first look at what sort of characterize a single y, the output. Okay, how does the output time series behaves over time? Is it a stationary one? Or is it a non-stationary one? And we study different types of descriptive models that could sort of, you know, fit into or captures this type of pattern that we've seen in one single series. Okay. Then after we've seen how we can model one single series, then we could move back to the usual regression case that we're familiar with. We're modeling different time series. Okay. Then we can take into account the labor and the capital input, and we model all of them together into a dynamic model. Okay. So what makes time series a bit more complicated is really the dependent structure within a single series, within the y itself. In cross-sectional, there's no such dependent structure between yi and yj, so it's sufficient to just model the relationship among different characteristics directly, just the y and the x. Whereas in time series, yt depends on yt minus 1, okay? And at the same time, it might also depend on x1 and x2. But because of this implicit dependent structure in one single time series itself, it makes sense to look at the dependent structure first before we take into account other time series. Okay? So this is the difference in terms of the analysis between time series and cross-section. So time series is just one step further. Because there's dependent structure within a single series, so we have to model that. And we also look at the stationarity, which is the core property of time series, and we hope that eventually we could sort of either transform our time series into a stationary one, or that we hope we'll just have a stationary time series at hand. Because stationary time series, they exhibit stable properties that allowed us to sort of easily capture the pattern, and that we could sort of make forecasts that is reliable building on the past pattern. And we define the weak stationarity as that if a time series has a constant mean over time, okay, if it has constant and finite variance over time, and that the covariance between any 2 points in time depends only on the distance between the 2 points, but not their absolute time index. If a time series satisfies all these 3 conditions, we say that it's weakly stationary. And you could just say it's stationary in our course, okay, because we are not looking at strict stationarity. Strict stationarity, as you see in the lecture notes, it's more of a technical assumption, but it's of little practical use because it just cannot be verified empirically. So the implications of having weak stationarity is that it allowed us to reliably estimate the properties of the statistical distribution. Okay? So if we had weak stationarity, that means the sample mean defined in the usual way, although now it's a sample mean over time rather than a sample mean over different individuals. So the sum is from t equal to 1 to capital T, which is the sample size of your time series, and that would, as usual, converge to the population expectation. And we will also have the sample variance converging to the population variance, and the sample covariance converging to the population covariance. These convergence only happens if we have stationary data, okay? And there's one thing to note here. In time series, typically we normalize the sum by 1 over t rather than adjusting for 1 over t minus 1 when we compute the variance, and similarly when we compute the covariances, okay? So this normalization doesn't really matter when we think about a large sample, because let's imagine 1 over 1,000 and 1 over 1,000 or what doesn't really have a huge difference, okay? So this correction ensures that we have unbiased estimates in large samples. So this is something, a slight difference compared to how we compute the sample variances and sample covariances in cross-section. Now, so before we move on, there's just a quick visual representation of why stationarity is important for estimating the statistical properties. So remember on Monday, we say that each time series is not a random sample, okay? Because we only observe one time series in the world, in this, let's say, in this universe. So the randomness doesn't come from random sampling as if in cross-sectional, but the randomness stems from the fact that imagine if there is multiple universe, okay? And that what happens in universe 1 will be different from what happens in universe 2, given that we have the same starting point. So imagine we all started here at time t equal to 0. That's the initial state, okay? So in the universe 1, which is where we're based, we observe the time series that evolves like this, okay? Just say, for example. Now, it could be that in universe 2, on day t equal to 1, a different event happens. Let's suppose this is just the stock price. Okay, a different event happens, let's say a different policy is announced, and that at t equal to 1, instead of the stock price being here, the stock price being here. And then on day t equal to 2, it will evolve to somewhere else. Then eventually, we will observe a different path for universe 2 that might look, for example, like this. Okay, so the red line represents universe 2. And this, the gray line represents the universe 1. And then for universe 3, it could be that something else happened as well, and we observe a totally different path. Let's say something like this. Okay, just for example. Now, one thing we could sort of see here is, regardless of which path we are on, they sort of fluctuate around the same constant over time, okay? And we could sort of also see that the fluctuation around the mean remains stable. So there's sort of, the fluctuation is sort of around the same range, okay? It's not that we have periods of high volatility followed by periods we have low volatility. And in this case, okay, let's consider just a random time. And this is t, okay? And what we're interested in is the expectation of y at time t. So thinking about the definition of random variable, essentially that is the weighted average of all the possible outcomes. Inherently, what we really want is the weighted average of all the possible outcomes that happens on this vertical line, okay? But we only observe one sample. We only observe one path, okay? So we want to estimate this point here. Let's say, okay, let's just use, using the observations along this line. But we only observe one point on this line. Okay, then how can we really estimate that point? With stationarity, okay, because the time series will fluctuate around the constant mean, then essentially the horizontal average will converge to the same value because they all center at the same value if we think about them vertically. Okay, so in a sense, stationarity ensures that the vertical property is the same as the horizontal property. But imagine if we have non-stationary time series. Okay, so in our universe, let's say if we have a non-stationary time series, on one day we started here. And in universe 2, we ended up here. And then maybe in universe 3, we'll end up something like this. Okay. Given the non-stationarity there, there is no way that if we look at this point, the mean might lie somewhere, say, here. Whereas if we look at a point here, the mean vertically might lie somewhere here. Okay, so when we have non-stationary time series, there's no way that we could estimate the vertical mean by taking the horizontal mean, which is why non-stationary time series will not give us reliable statistical estimations about the true underlying statistical properties of the time series itself. So essentially, we want something that looks like this. Therefore, we could use the horizontal properties to estimate the vertical properties. Okay, that is why we care about stationarity. So this is just a sort of a visual representation of the intuition or the motivation underlies why we care so much about stationarity. In more advanced time series courses, you get to learn more about this in mathematical way. So coming back to our lecture slide. So we also talk about the autocorrelation function on Monday. So essentially, it's just a correlation function, but it's about the correlation between the time series and itself, let it be the past or the future. And the correlation defined in the usual way is just the covariance between the two random variables over the square root of the product of their individual variance. Now, we know that given we have a stationary process, the covariance, which is the numerator, depends only on the distance, which is what we call gamma h, okay? And we also know that the variance of a stationary process is constant over time. So the variance of yt is the same as the variance of yt minus h. Therefore, the product of them is just the square root, it's just the square of the variance yt. Taking the square root, you simply have the variance of yt in the denominator. So essentially, for stationary processes, the autocorrelation, just like the autocovariance, depends only on the distance between the two random variables. So it quantifies the correlation between yt and its h lag if we're thinking about rho h. Now, one thing you have to be careful with is the difference between autocorrelation and autocovariance. Okay? Autocovariance does not measure the strength of the linear relationship. Okay, remember, autocovariance is sensitive to the unit of measurement, whereas the correlation itself is a unitless measure. Okay, it's already standardized by the unit of measurement. So the magnitude of the correlation will tell us the strength of the linear relationship, whereas the magnitude of the covariance does not tell us anything about the strength of the relationship. Okay? So the correlation is strictly bounded by -1 and 1. Okay? If we have the rho of H being equal to -1, it means that they're perfectly negatively correlated, whereas if it's equal to 1, it just means that they're perfectly positively correlated. And if the autocorrelation is 0, it just implies there's no zero correlation. And importantly, for H equal to 0, so we're looking at rho of 0, that is essentially the correlation of YT with itself, because the distance between a point with another point that is 0 distance, that is exactly itself, the correlation with itself is perfect, okay, which is equal to 1. So the rho of 0 is always equal to 1. And we can also consistently estimate the autocorrelation function by the sample of ACF, okay, which is just by plugging in the sample autocovariance and the sample variance. And under stationarity, it also converges to the population autocorrelation function. So ACF is the short for autocorrelation function. Whenever you see ACF in the econometrics literature, it's actually referring to the autocorrelation function. Now, the autocorrelation function is a very important measure because it relates to a term that we call persistence. So basically, persistence is about the series memory, the rate at which the autocorrelation decays, okay? So in general, stationary series will have very weak persistence. So initially, the correlation among the YT with YT, let's say -1, and YT -2 might be quite high, okay? But the autocorrelation will decline very quickly as the distance increases, okay? Meaning that the correlation are short-lived. So there is very weak or limited persistence. And this is essentially what it means by constant mean, okay? Imagine if they're fluctuating around the constant mean, it must imply that they tend to revert to their mean, okay? If there is a strong persistence, if the memory is, if it has a very long memory about its own past, let's say the past influences the future a lot, then in that case, it's very hard for it to fluctuate around the constant mean, okay? Because a positive value will tend to be followed by another positive value, and another positive value will tend to be followed by another positive value. So you see a trend rather than reverting to the constant mean, okay? So stationary series will tend to revert to the mean because it has very limited persistence, and that allows it to have a constant mean. Whereas strong persistence, okay, usually indicated by a slowly decreasing autocorrelation function, that's hinting on non-stationarity, okay? So here we can see the graphical illustration of how the ACF differs for stationary and non-stationary time series. So on the left, we have the quarterly real GDP. On the right, we have the GDP growth rate. So basically, the growth rate is just the difference real GDP. Okay? It's the difference between today and yesterday that gives you the growth rate. And before we look at the two plots closely, so you might observe that on the ACF plot, there are the blue dashed lines, okay? So essentially, the blue dashed lines on each ACF plot gives a 95% confidence interval. It's the 95% confidence interval for testing the statistical significance of the autocorrelation at a given lag. Okay, so let's just focus on one ACF. So the vertical axis gives you the magnitude of the ACF, and the horizontal axis gives you the lag that we're looking at. So the number 1, 2, 3, 4, 5 stands for annual data. And because here we're looking at quarter data, so here the first line or the first spike stands for lag of 1, so 1 quarter. So let's say this is today, this is 1 quarter ago, that it's 2 quarter ago, the line here, this stands for 3 quarter ago, and that the line where you have 1 on the horizontal axis stands for 4 quarters ago, which is 1 year ago, okay? And the height of each line basically tells us the magnitude of the ACF. And remember, the ACF is 1 for 0 distance. When lag is equal to 0, essentially that ACF is just the correlation of YT with itself, which is why in every sample ACF, the first vertical line always have height that is equal to 1, okay? And it's always the case that the ACF is bounded by 1 and minus 1 because correlation is bounded by 1 and minus 1, okay? So back to the blue dashed line, therefore testing the hypothesis that the autocorrelation at a given lag is equal to 0. So we can see here all these lines, they exceed the 95% confidence band, which means the ACF at the given lag is statistically different from 0. So taking the lag 1 line, okay, we can see that this is very high, almost close to 1. So, and it exceeds the blue dashed line, meaning the ACF at lag 1, which is row 1, is statistically significant at 5%, okay? And similarly for lags of all lengths. Whereas on this ACF plot, okay, we can see that for 1 here, this is inside the blue dashed line, okay? And this is the lag of 4 because this is the first lag here, this is the second lag here, and we have the third lag here and the fourth lag here, okay? So row 4 is statistically insignificant at 5%, okay, which means that row 4 is not statistically different from 0 at the 5% significance level because it's inside the blue dashed line, okay? That's how you read the ACF plot. If it exceeds, if it's outside of the blue dashed line, it's statistically different from 0. If it's inside, it's not statistically different from 0, okay, at the given lag. So basically, this is how you read the ACF. And we can see that the real GDP, the plot on the left, has an upward trend, okay? And clearly, the mean is changing over time, which means it's not stationary. And we can see that the sample ACF plot, okay, the ACF is declining very slowly as we increase age, which indicates the strong persistence, okay? So this is supportive for what we have observed in a time plot, okay? So this is non-stationary. Whereas on the right, where we're looking at the growth rate, so we can sort of see that it's fluctuating around a constant mean, although it seems like the volatility, okay, doesn't really be constant over time. However, this is definitely more stable than the real GDP. So arguably, it's stationary. And if we look at the ACF plot, okay, so we can see that except for the first 2 lags, which is outside of the confidence bands, the rest, they are all within the blue dashed lines, meaning that they are statistically insignificant. So while we have 2 statistical significance ACF for the initial lags, okay, the rest are all insignificant, meaning that the ACF functions drops very rapidly, okay? So there is little persistence in the growth rates, which is another evidence of stationarity, okay? So here we can sort of see that the growth rate is more stable than the GDP itself. So one way that we could sort of stabilize a non-stationary time series is by taking the difference, okay, by differencing. Taking the difference between today and yesterday, or here, since it's quarterly data, basically it's taking the difference between 2 quarters, okay? So this is stationarity and persistence. So essentially, what we've sort of discussed so far is that how can we determine stationarity in time series? So we look at the visual inspections, okay? So we've seen how we can sort of identify patterns of trends or varying volatility in a time plot, and these help us identify whether they are stationary just in a visual way. But this is not formal analysis. Okay, the next step, we will see using more formal ways to establish stationarity. Okay, either by looking at a sample ACF, we've already looked at. Another way is by comparing the means and variances across different time periods and check whether they're constant over time. Okay, let's imagine if we take the quarter data from 1980 to 2000, and we also take the quarterly data from 2000 and 2020, you can compute the mean, the variances in the 2 different samples and check if they're similar. And that's also another way to kind of inform, more formally than a visual inspection, okay, but still a little bit informal. So later in maybe week 4, we'll discuss statistical tests that are specifically designed to detect non-stationarity, something we call the unit root test or the Dickey-Fuller test. And if we know that the underlying time series is stationary, then we can go ahead and sort of model it in the usual sense. Okay? The conventional T statistics, the confidence intervals, the F statistics, they can all be interpreted in a way as we've done in cross-section. So that is the stationarity. And given we know a bit about these properties, so next we'll look into how we can model time series process depending on the pattern that we observe in the underlying data. So remember, the focus of this course is about forecasting. So we only want to establish descriptive models. We don't care about the causal mechanism. We only want to establish descriptive models that captures the underlying pattern well. Okay? This model might not be exactly the same as the causal mechanism that generates the time series, but as long as it fits the observed pattern well, it's a good descriptive model. So typically, we'll discuss 3 types of time series processes that we've seen in time series. That's sort of the fundamental processes. The first one is white noise. Okay? This is something very similar to the IID error term that we've seen in cross-sectional or in traditional regression analysis. This is the basis for any complex time series models. Okay? Any complicated or more complex time series model must have a white noise component. So one important feature about white noise is that it's inherently stationary. White noise, it's always stationary. So this we'll be discussing in a bit. And then we'll also look into a type of process called autoregressive models. Okay, so autoregressive, it's defined similar to autocorrelation or autocovariance. Basically, we're regressing Y on its own path, okay? And typically, this is denoted as ARP, stands for an autoregressive model of order P. The order means how many paths we have included into the model equation. So let's say if we're looking at an AR1, then essentially we're including one path in the immediate path into the model equation. So we're regressing YT on YT minus 1, okay? If we have an AR2, that means we include the first 2 immediate lags into the model equation. We regress YT on YT minus 1, YT minus 2, okay? So if the P lag, so we start from 1, 2, all the way to the P lag. Now, different from white noise, which is inherently stationary, the stationarity of an AR process depends on the coefficients on the flags, okay? So it depends on whether the slope coefficients are within certain bounds. Then, for example, for an AR1, the stationarity of an AR1 depends crucially on the magnitude of alpha 1, which we'll see next week, okay? And another type of model that we commonly see in time series is what we call a moving average model. So instead of regressing y on its own past, we regress y on the past of an error term, okay? So a moving average of order q means that we regress y on q past error term. So for example, MA1, we will regress yt on the first lag of the error term, okay? So essentially, a moving average model is a weighted average of all past error terms. You won't see a past y on the right-hand side. So I won't be discussing the moving average model during the lectures, so you have to read the lecture notes yourself and exercises. But the analysis for moving average is analogous as a white noise and autoregressive model. Essentially, we're looking at the statistical properties. Another reason why I won't be really covering moving average during the lecture is that if we look at the moving average model, everything on the right-hand side is not observable. We never observe the error term, okay? The UT, the UT minus 1, these are what we call innovations or disturbance in time series because they represent shocks, okay? These error terms are not observable, which means traditional estimation method like the OLS that we've seen last term would fail to estimate this type of model. In order to estimate MA models, we either need to do some nonlinear transformation or we need to impose some further assumptions, okay? And these would require techniques like nonlinear least squares or maximum likelihood estimation that I won't be covering in our course. These will be typically covered in more advanced level econometrics courses, which is why I'm not going to talk a lot about MA models. But one thing you should know about the moving average model is that it's always stationary for a finite number of Q. And why this is the case, check the lecture notes and the homework exercises, okay? Do attempt the homework exercises. They are very, very important for your understanding of the lecture material and also for preparing the exams, okay? So I think we're kind of running out of time. I think I'll just stop here. Next week, we'll start fresh on discussing the white noise and AR models. So I don't think I'll have time this term to cover the limited dependent variables, okay, because I'm still writing my lecture notes. So one thing about the lecture notes is, hold on, where's my lecture notes? So I will upload the lecture notes for the first 2 chapters of time series on Blackboard, maybe later today. I'm still writing it. There are like, how many? So we have a total of 6 chapters for time series. I will upload the rest once they are ready, but the first 2 will be sufficient for the reading for this week, next week, and possibly even week 3's lectures, okay? So they will be available sometime today or tomorrow. Thank you for coming and have a good weekend. I'll see you guys next Monday at 9. Oh, by the way, one last thing. And so Sophia, your lecturer for managerial economics, have asked me to advertise this event that's happening next Wednesday. And yeah, maybe scan the QR code if you're interested in. It's about, career and employability conference, which given that you're either in your 2nd or 3rd year, I think it will be beneficial.